The
Thermodynamic law 2.
no,
And
we
then,
Ohm's law,
yes, ma'am. I was
isn't
in
it?
middle part. Yes.
Yeah. So we were doing Ohm's law, in which I had told you about the ohmic and the non-ohmic conductor. So there are some conductors which follow the straight rule, that is linear relationship between the current and the voltage. Okay. Whereas there are some conductors which does not follow it directly, but they are showing the graph like this. Okay. Due to their high resistance. Understood?
Yes, ma'am.
Okay. So due to this, they basically show a non-ohmic property also. Okay. So ohmic conductors are those conductors which follow the rule V is directly proportional to I. Okay. Whereas here in non-ohmic conductors, they obey the Ohm's law for basically a very linear time period. I should say a very small time period. Let's say this much only. Okay. And after that, they do not show. Like if I give a talk about a light bulb filament, okay, that is an example of a non-ohmic conductor. Done?
Yes, ma'am.
Okay. Then the reason behind this is the current flows through the basically if I'm taking an example of the light filament bulb, then the current is flowing through the bulb and electrical energy is transferred to the thermal energy. Okay, which basically result in the increase in the temperature and it leads to the increase in resistance. Understood?
Yes, ma'am.
Okay. And hence they are not following the Ohm's law and ultimately they will become stabilized after a certain limit of the time and they will show you a straight graph. Any doubts?
No, ma'am.
Sure?
Yes, ma'am.
Okay. Now after this we are having the next topic and that is electric cell and the batteries. So obviously you are aware of the electric cell and the batteries and yesterday I had given a talk about EMF etc. things. Okay. So there are
Yes.
two particular things with us. One is EMF and one is voltage. Okay. Now try to understand this particular factor that if suppose this is my circuit and here I am having a resistance of let's say 5 ohm and I am connecting it with a battery. Okay. And the battery is connected something like this and here I am measuring it with the voltmeter, the voltage that is coming. Let's say it is of 2 volt. Okay. So while you are measuring it, you will observe that not the complete 2 voltage is flowing through the circuit. Okay. What is happening over here is let's just find out first how much current is flowing. So V equals to IR. Okay. V is 2. I is how much? We have to find. R is how much? 5. Correct. So I will be equal to 2 over 5. So what is the amount of current that is flowing here? Tell me. Akshita, are you
1
there?
second.
Yeah. Be quick.
0.4.
0.4. So that means through here 0.4 ampere of current should flow. Okay. But
Yes.
when we exactly, sorry, when we exactly measure it, we observe that only 0.38 ampere it will show, or let's say 0.35 ampere it will show. So where is this 0.05 ampere is going? That is the question now. So what happens here is the battery is also doing the work, okay, in converting the chemical energy into electrical energy. Okay, that particular work done, we call it as resistance. Understood or not?
Yes, ma'am.
For this device. Any doubts?
No, ma'am.
Okay. So here what happens is a particular small R I am adding. Okay. That is this particular circuit is also using some of the resistance to convert the energy from chemical. Obviously, when you are giving the 100% efficiency, you are supplying 100% of the fuel to a given engine, it will use some of the oil or fuel to convert the uh, fuel energy into whatever you are doing, let's say mechanical work. A machine is doing some mechanical work. Okay. So into mechanical energy. Understood? And hence you will get the efficiency as 95%. Okay. Not 100% of the petrol is used to drive the car. Some of them it's used in converting and it's in the engine. By the engine it has been used. Correct? So you will
Yes.
get only 95% of the efficiency. So there is no engine in the universe that can give you 100% of the efficiency. So similarly, if we take and if we consider the cell is also a kind of machine only, and if it is using some of the current, are you getting?
Yes.
Yeah.
Yes, ma'am.
So it will use some of the voltage in converting, that is the chemical energy, into the charges, and it will create a high potential over here and low potential over here. Making sense?
Yes, ma'am.
Okay. Now this high potential, that is plus energy, and minus that is low potential energy, the charges will start flowing in this particular circuit like this. Okay. And you will observe that out of 2 voltage, only 1.8 voltage is flowing through this circuit. So here I will be getting only 1.8 voltage, which has been calculated by the voltmeter. Okay. So now here the question is, the total energy which is shown by the battery, that is 2 volt, is known as the EMF of the battery. It is not the voltage. EMF meaning the total market value of the voltage which is supplied by the company. Okay.
Yes, ma'am.
Okay. Whereas the 1.8 voltage, that is exactly we are getting, is known as terminal potential difference. Getting?
Yes, ma'am.
Okay, so this terminal potential is 1.8 volt. Now this is known as the voltage of the circuit. Okay, so when you are calculating the total EMF of the circuit, you need to add the current that is flowing through the battery as well as the current that is flowing through the resistance. Now you will going to get the complete EMF of the circuit. Making sense?
Yes. Yes, ma'am.
So the formula is EMF equals to R plus R. It's very, very important, and many a times it comes in the exam. Any doubts?
No, ma'am.
Okay. Now after this, we are having generator. Okay. You are aware of generator. We have studied this in the grade 10 class.
Yes, ma'am.
Okay. I will be just repeating its mechanism and the working. Okay. So the generator, it depends upon the principle of converting your mechanical energy into electrical energy, and it uses the electromagnetic induction phenomena. Making sense?
Yes,
Okay.
ma'am.
What do we do in electromagnetic induction? Suppose here we have the magnet, that is north pole and the south pole. Here I am keeping a rectangular coil. Okay. And this rectangular, through this rectangular coil, let's say the brush has been connected and the current is flowing through the circuit. Then what will be happening over here is, suppose here is the key and I had connected this key now. So what will be happening is, okay, here we do not provide the battery, but here we provide the galvanometer. Okay, galvanometer detects the amount of current flowing through the circuit. Okay, so now here is the key. As soon I switch on this key, what happens is, here we are connecting a spindle. Okay, in this circular region, and the spindle, where as soon it rotates with the help of any fuel, what happens is this mechanical energy creates a rotational motion of coil inside this north and south pole. Okay, so the force of rotation is cutting the magnetic field at 90 degree. Making sense? And when we
Yes.
apply the Fleming's right hand rule, try to understand this factor. When we apply Fleming's right hand rule, that is if suppose this is my thumb, this is one finger, and let's say this is the third finger. Okay, so if this is your thumb, this is your forefinger, and this is your center finger. Okay, the thumb gives the direction of the force of rotation. Forefinger gives the direction of the magnetic field. Then it gives the direction of induced current or okay. So this will give you the direction of either induced current or induced EMF. EMF is the voltage when you are applying the voltage in open circuit. Remember, no?
Yes, ma'am.
Okay. So please
Yes.
remember these factors. Otherwise it
Okay.
will be tough. Okay. So I'm saying that if it rotates applying Fleming's right hand rule, then it will generate current. What is the rule? That if you are supplying the magnetic field at 90 degree of the force of rotation, in the third direction you will get induced current. Understood?
Yes.
So hence
Yes.
as the circuit is closed, induced current is developed. And if the circuit is open, induced EMF you will get, because EMF is the voltage only but in the open circuit. Okay.
Yes, ma'am.
Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay. So here I am getting the current in this direction and it will be detected through the galvanometer that it measures the current in even microamperes. Okay.
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. Now I am moving to the next thing, and that is your photovoltaic cell. Now, what is photovoltaic cell? It is a semiconductor device that is based upon the PN junction. Okay. And it transfers the solar energy. You are aware of PN junction,
Yes.
no?
Yes, ma'am.
Okay. Into electrical energy. Okay. And a PN junction is a slice of the semiconductor over here. Okay. Where one side has been doped with the impurities of holes and the other side is doped with the impurities of electrons. Okay. So if suppose
Yes,
this
ma'am.
is my P type and here I've been having the doped part and here I am having the N junction. Let's say this is P type. Let's say this is N type. So here I'll be having all the electrons collected because P type stands for positive. So it will be attracted with the electrons, whereas N type will get attracted with the holes. Okay.
Yes, ma'am.
Done? Yeah. So at the junction between the P and N or N and P, you will get the electrons and the holes that are migrating to give the region of electric field. So here I got a region of electric field. Done?
Yes, ma'am.
Okay. Now what happens is, as the light incidents upon the, wait, will be more easier for you. Check. Can you see this picture?
Yes, ma'am.
Okay. Now, as the light is incident on the N type of the semiconductor, what happens is it causes more free electrons. Okay. And that helps in giving the photovoltaic effect. Are you getting?
Yes, ma'am.
See, this is the top layer contact with the resistor. It is connected with the bottom layer. The bottom layer is basically your N junction. The top layer is your P junction. You can see the plus and minus layers over here. Okay, and this is the anti-reflective layer over it, which does not reflect back the light radiations and it absorbs the light. Hence, it will create more of the free electrons. Getting?
Yes, ma'am. Yes,
Okay.
ma'am.
So what happens is the top contact does not cover the whole top and it leaves some space. Okay. And for the light to get into the PN junction, you can see the top contacts here. Okay, and the silicon is very shiny, so anti-reflective layer has been created, added to it, so that it will reduce the energy loss done by reflection, and hence the light reflecting off the top layer is very thin film undergoes the phase change of pi, and it creates a light reflected at the bottom layer. Okay, and the light actually give out, I should say, the free electrons. Making sense? So see here the light is incidenting. Due to anti-reflective coating, what happens is it will go inside and it will not come out. Okay, so reflection is not happening. Okay, observed? Clear?
Yes, ma'am.
Any doubts?
No, ma'am.
Sure?
Yes, ma'am.
Okay, moving for the next topic, that is power has been already discussed, power dissipated is already discussed. Now a very important topic that is remaining, last one, and energy we calculate in electron volt, in kilowatt hour, and also in joules. I'll explain all these terms one by one. You have to pay attention. It could be asked in any how way. Okay. So now what is 1 electron volt? The energy captured by 1 electron, that is 1.6 into 10 raised to minus 19. Okay. Joules will be having in 1 electron into 1 volt of the energy. Making sense? So this is the basic conversion. Any doubts?
No, ma'am.
Okay, let's come to kilowatt hour. So basically, when your power is calculated in kilowatt and your time is calculated in hours, then combinedly you will get kilowatt hour. Okay, so if I say 1 kilowatt hour, it will be 1000 watts into 3600 seconds. When I combinedly write it, it will be 3.6 into 10 raised to 6 joules. So this is the conversion of kilowatt hours to joules. Okay. Third unit is joules. So in joules, you calculate your energy in such a way that your power is always calculated in watts, whereas your time is always calculated in seconds. Any doubts?
No, ma'am.
Sure?
Yes, ma'am.
Okay. Any of the three things can come and you do not have to scare about this particular topic. Okay?
Okay, ma'am.
Done. Do you need me to explain electric motor of grade 10 or you are aware?
Yes, ma'am. I am aware, ma'am.
Okay. Then I am going for the combination of the components.
Yes, ma'am.
So, yesterday you had taken a lot of time in understanding that part. Carnot engine and Carnot cycle. Okay. Fine. Now, no issues in that, but okay. Let's come to this. So, here we are having resistors in series. So, that is R1 plus R2. Here what happens is your always current remains same. Okay. And here your voltage.
Voltage changes.
Yeah, it varies. And your resistance equivalent, this is resistance equivalent, no, is always higher than component, or I should say, let me write R1 and R2. Okay, separately R1 and R2, it will be always higher. Done. So resistance is always high in this particular circuit. Whereas if I write 1 over R equivalent, the answer would be 1 over R1 and 1 over R2. Any doubts?
No, ma'am.
Okay, so this will going to give you the current always varies voltage remains
Voltage
the
is same.
same, whereas your R equivalent will always be lesser than separately R1 and R2.
Yes,
Making
ma'am.
sense? And
Yes,
in the
ma'am.
last, you have to reciprocate this answer.
Yes,
Done?
ma'am. Yes, ma'am.
Okay. Now, after this, we are having the cells in series. Okay. So, when you are having the cell in series, you will add the EMF as EMF1 plus EMF2. Okay. And you will apply the simple formula, that is EMF equals to IR plus IR. Okay.
Yes, ma'am.
This is the voltage of the cell and this is the voltage of the circuit. Making sense?
Yes, ma'am.
Okay. Now let's talk about the parallel connection. So in parallel, you will always have 1 over EMF 1 equals to 1 over EMF 2 and 1 over EMF 2. Okay. Wait. Let me write. 1 over EMF 1 plus 1 over EMF 2. Any doubts?
No, ma'am.
Okay. Now, when you have LDR circuits, what does the LDR circuit do? It depends upon the resistance. First thing. Okay. Now, when it varies, let me show you the particular symbol of that may come in exam. Okay. So, the symbol for this particular circuit is something like this. Okay. Light dependent resistor. Okay.
Yes, ma'am.
Okay. So here in light dependent resistor, it has a very high resistance and it vary as the light intensity falling on it changes. Getting?
Yes, ma'am.
It
Yes, ma'am.
has a resistance that vary as the light intensity falling on it changes. Understood?
Yes, ma'am.
Okay, now this is a semiconductor device again, and here the light causes the release of more charges again. So more charge carriers in the semiconductor, which results in the lowering of the resistance.
Yes, ma'am.
Okay, and if anyhow we have used the light gate. Do you know what is light gate?
One second. Light gate is light gate. No, ma'am. I haven't heard the term like light.
Okay, so in the light gate, it includes the LDR topic. Okay, it have the LDR topic. Let me show you the light gate also. Check. This is how it looks like. Okay.
Ma'am?
I'm showing you the pictures. Don't worry. I'm here.
Okay, ma'am.
See. Okay. Here, when the voltage is given, here LDR is included. Okay. And here variable resistor is included. So here it will give you light gate. Okay. This is light gate. Understood? Any doubts?
No, ma'am.
Sure?
Yes, ma'am.
Okay. Now after this, we are having, yeah, it includes light gate and it changes the resistance. Okay, in light gate, you have to remember that it low down the resistance. Okay, the light causes the release of more charge carriers, which is responsible for the flow of current, and it will lower down the resistance. It emits the light, it captures the light. Understood? Please don't forget this. It
Okay, ma'am.
releases more charge carriers. That charge carriers result in the semiconductor it releases, which result in the higher current and lower resistance. Done. Now after this, we are having the topic that is thermistor. What does the thermistor do? Thermistor is having the symbol like this. Okay, and the line is straight. Okay, so in thermistor also it is a semiconductor device. Okay, but rather than the conductors, okay, unlike the conductors whose resistance increases with temperature, and due to increased lattice vibration it happens, and the resistance of semiconductor, what happens in the semiconductor, the resistance of the semiconductor decrease as the temperature increase. Okay, this is due to increase in charge carrier. Understood?
Yes, ma'am.
Okay, so this is the particular topic. Now after this, we are having new topic, and that is wave behavior. Okay, now please focus what is wave behavior. So wave is nothing but a disturbance in the medium. Okay, suppose here I am having the particles and you are supplying some energy in the medium. What it will do? It will create a wave. What is wave? Basically, the particles which are aligned in one line, they will be vibrating, and the collision of each other will create a wave. Because in our eyes, if 10 frames per microseconds is passing, then we will observe that object to be moving or in the motion. Done. So the particles are vibrating in a very huge speed, which basically gives you that it is moving like a wave. For example, we are having electromagnetic wave. So electromagnetic wave is a combination of electric field and magnetic field.
Magnetic.
Then in the third direction, you will get your electromagnetic wave, which is nothing but your light.
Yes,
Okay.
ma'am.
So
Yes.
all the EM spectrum, that is your X-ray, your gamma ray, done. Then your ultraviolet ray, infrared ray, then your visible range. All these range show the same picture. It's just that their frequency and their wavelength vary with each other. Okay, understood now?
Yes, ma'am.
Okay, done. Now let's pay attention over here. When we are having the simple pendulum with us, we can compare the wave with this wave behavior. Okay, just pay attention. If suppose this is my simple pendulum and it goes like this, it comes back and it goes like this. Okay, so when it's reaching the height, okay, when it reaches the height, basically here the potential energy is at its maximum because it is carrying a height, where M and G are constant terminologies. Okay.
Yes, ma'am.
Okay, hence so height is increasing, so potential energy is highest at the left extreme point. Similarly, at the right extreme point also, your potential energy is very, very high. Done? So
Yes.
if I take the mean position, in mean position, obviously your wave is, when it is coming back and it reaches here, what happens is it will push the particular wave to go in this direction, and hence it is going in the right hand side also. Otherwise it should stop here. Correct? The velocity
Yes,
is very high, hence the mv square, half mv square, nothing but the kinetic energy is at its highest at the mean position. So in the thorough mechanism, we are observing that the total mechanical energy is the combo of potential plus kinetic energy. Done?
Yes, ma'am.
Any doubts?
No, ma'am.
Great. Now listen. So similarly, this is what happens if this is my wave. This is the mean position. It goes like this. It reaches the left extreme point. It comes back.
Yes, ma'am.
Okay. Then it comes back to the mean position. Again, it reaches this point, right extreme point. Again, it comes back. Okay.
Yes, ma'am.
Let's compare this with a circular motion now. If I am starting my motion from here, let's say A position, I have reached this position, let's say B. So I had covered S distance. When I observe it while standing on the center of the circle, I have covered theta distance. So my theta distance is your angular displacement. Whereas S is your linear displacement. Understood?
Yes, ma'am.
Okay, so now this is 0, this is 90. This is 0, this is 90. Correct? 90 to 180. Here again I am coming back. So here it is 180. Let's go in the negative cycle. This will be 270. Let's go in the negative cycle. It will be 270. Again coming back. You are having 360-degree angle completed. Making
Yes,
sense?
ma'am.
So
Yes, ma'am.
circular motion is also a kind of wave only.
Yes, ma'am.
Okay, any doubts?
No, ma'am.
Okay, now after this, pay attention. If I am calculating the distance theta, then to calculate any angle, that formula is arc over radius. Correct?
Yes, ma'am.
So what is the arc that I had covered? I had covered S distance. What is the radius I had covered? It will be R. So the formula that I got over here is theta equals to S over R, or even you can say S equals to theta times R. So this is a relationship between the linear displacement and the angular displacement. Understood?
Yes, ma'am.
Any doubts?
No, ma'am.
Similarly, you can say your V will be equals to omega times R, where omega is your angular velocity and V will be your linear velocity.
Yes, ma'am.
Making sense?
Yes, ma'am.
Okay. So if suppose I am covering the thorough circle distance, so it will be 2 pi R. Correct?
Yes, ma'am.
And here all the distance that I had, radius I had traveled is R. So R and R will cancelled out and theta will be equal to my 2 pi radian. You have to calculate it in radians. Any doubts, Akshita?
No, ma'am. No, ma'am.
Sure, you are notifying everything, no?
Yes, ma'am.
Done. So after this, 1 radian is having the value of 56.7 degree in your protector. This is the conversion that you are having.
Yes, ma'am.
Any doubts?
No, ma'am.
Sure?
Yes, ma'am.
Done. So after this, what we are having? How to calculate omega. Omega you calculate delta theta over delta t. Similar way as V equals to delta S over delta t. Check. Both of them are same. Nothing is different. It's just that this is linear and this is angular. Correct?
Yes, ma'am.
Are you facing doubts, Akshita?
No, ma'am. No.
It's clear, no?
Yes, ma'am. It's clear, ma'am.
Done. So hence, we are also having the formula of angular velocity as 2 pi f, because theta covered is 2 pi. Isn't it? Theta covered is 2 pi angle. How much time it is taking? Let's say capital T for the one oscillation. Done. So 2 pi over T, and we are aware f equals to 1 over T. Hence we can say omega equals to 2 pi f or 2 pi over T. Any doubts?
No, ma'am.
Sure. Understood everything?
Yes, ma'am.
Okay. Now next
I think
topic
I know,
is
like these stuff.
you are aware of. Very good. Then after this we are having simple harmonic motion. Okay, now pay attention. What is simple harmonic motion or your SHM? Okay, so basically, let's say I am having an ant which is traveling over a hill. It's taken 1 second. It stayed over there. It stayed over there. Then it came back. It fallen down for next 1 second. Again, it had taken the rest for 1 second, gone on the hill. Again, it had taken a rest over the hill, but it fallen again. Okay. So the whole thing is happening in 1 second. So this particular event is known as periodic motion. Over a period of time where the time span is fixed and the motion has been repeating itself, this is known as periodic motion. Any doubts?
Yes, ma'am. No, ma'am.
Okay. Now after this, let's put a constraint. I am putting a constraint that my object should go only to and forth while performing the repeated motion. So it is going to and forth. Okay. So this constraint I am putting. So this particular motion is known as oscillatory motion. Understood?
Yes, ma'am.
Let's put one more constraint over this, that it should be covering only one unit distance over this side and one unit distance over this side. Okay. So now it will be known as your SHM.
Yes, ma'am.
Any doubts?
No, ma'am.
This you can perform in force mass system. I should not say force and mass, but spring mass system. Okay. In spring mass system also you can observe this particular thing happening. Suppose here it is fixed and here I am having a spring, here I am occupying a mass. You will be applying a deforming force, it will try to come back. So let's say the unit distance it is covering, the extension is just of unit distance. So F equals to minus kx is the formula. Here your k is fixed and your x is just 1 unit. Done. So that means
Yes.
I am providing a condition where F will be equal to minus k. This is known as SHM equation. Any doubts?
No, ma'am.
Done. Now, when it is moving forward and coming back, it will be performing a wave equation, and that wave equation is given as SHM equation, which is nothing but A sine omega t. So the displacement of the wave at a given time is given by A sine omega t, where omega t, sine omega t is your phase angle. Phase angle is the angle which is giving you the start position of any wave. Understood?
Yes, ma'am.
A is the amplitude.
Yes, ma'am.
Y is the displacement of wave at that given time. Any doubts?
No, ma'am.
Understood everything?
Yes, ma'am.
Okay. Now, SHM and sine function play a very, very important role. Okay. Let's say at 0 seconds if I am checking. So at 0 second, that is at the start, the displacement will be 0 and the velocity will be maximum. Okay.
Yes, ma'am.
Okay, let me show you the positions, then you will be able to align it very clearly. Akshita, are you understanding each and every term?
Yes, ma'am.
Any doubts that you are facing?
No, ma'am.
Okay. Check this picture. Now I am explaining, just check what is happening. So at the 0 second, I am explaining here. 0 second. Okay. The displacement is 0, velocity is maximum, and it is having a positive gradient. Done?
Yes, ma'am.
Okay. The basically, if I compare it with the pendulum, then the bob will go towards the positive side. Done. And here, let's say at first second, I am calculating now. So the displacement is maximum. It is positive, and the velocity now has reduced to 0. Understood? Therefore, it will come
Yes.
back. Okay.
Yes, ma'am.
Now, let's come to second position. Second pay. Here the displacement is 0 again and the velocity is maximum again, but now it will go towards the negative side.
Yes,
Correct?
ma'am. Yes,
Done.
ma'am.
Let's come to third second. At the third second, the displacement is maximum, but it will be in the negative cycle and its velocity will be 0. Clear?
Yes, ma'am.
Let's come to fourth second. Again, it had came to the start position. Any doubts?
No, ma'am.
Okay. Now, after this, we are having the equation of SHM, which I had already explained you. Okay. In the terms of this, you can also write it as x equals to x naught sine omega t, omega equals to 2 pi f. So, in exam, as per the demand of the question, you can also apply 2 pi f into t. If I am writing small t basically indicates the half equation part. Okay. Capital T indicates
Yes.
full part. Done? Any doubts?
No.
Sure.
Yes, ma'am.
Okay. Now the same thing you can apply to spring mass system also. Okay.
Yes,
Shall
ma'am.
I show you that?
Yes, ma'am. You-
Check. This is spring mass system now. Okay. First it was
Yes.
at its compressive position. It got compressed.
Extension.
Okay.
And then compression.
It got compressed. Now it had got elongated.
Yes, ma'am.
Now it is at normal position.
Yes, ma'am.
Okay.
Yes, ma'am.
And again it got stretched. So this is stretching E plus X. This is compression E minus X. It is normal position due to mass where mg is balancing your tension force, that is Kx. Any doubts?
No, ma'am.
Sure?
Yes, ma'am.
Okay. So the final equation you will write it as that your where is your acceleration is happening. So F total equals to ma from Newton's second law. Done. So your ma will be equal to what? Either it will be mg plus kx or it could be minus mg also. So it will be finally kx. So your final acceleration you will calculate as kx. Plus mg is for this, minus mg is for this. Any doubts?
No, ma'am.
Shall I solve this?
Yes, ma'am.
Okay. Check. My ma will be, I'm writing here, for mg minus k e minus x. For which position I'm writing? Tell me.
For the compression.
Yes, for compression. Okay. Where
Yes.
I'm compressing in this direction. So this direction
Yes.
will be my positive direction and mg is hanging in this direction. Okay. So where
Yes,
is your
ma'am.
acceleration direction happening?
Down.
Down. Okay. So this will be plus and this will be minus. Any doubts?
No, ma'am.
Similar way, you can also write mg minus, I'm just solving this now. Okay. Just check any doubts if you are facing.
Yes, ma'am.
Okay. Done.
Yes, ma'am.
So here mg equals to this much. Okay. Mg minus ke plus kx. So what is the value of your ke? In the first position it was mg.
Yes,
Check.
ma'am.
Your ke,
Yes, ma'am.
your kx here in this position, sorry, my bad. In the second picture, you will observe that your ke is balanced by mg, correct?
Yes, ma'am.
Done. So your ke is mg. So here I can replace mg. So I'll be writing mg minus mg plus kx. It will get cancelled out. Hence my ma will be kx. Clear?
Yes, ma'am. Yes, ma'am.
Okay. Now this was done for the position 3. Clear?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Okay.
Clear, ma'am.
Okay. Now let's solve for 4th position. Same way you can go for 4th position also. That your MA is equal to KE plus X minus MG. Check.
Yes, ma'am. Because
KE
actually,
plus X minus MG will be your MA.
yes,
Because
ma'am.
when you will be stretching, it will be going up. So acceleration will be upward.
Yes, ma'am.
Any doubts?
No, ma'am.
Okay. So hence it will be nothing but KE plus KX minus MG. Again, I will apply the same thing. KE is MG. So here I will be writing MG plus KX minus MG. MG cancel. Again, I will get what? Finally, that my final acceleration is KX. Understood the thorough scenario?
Yes, ma'am.
Okay, so when the displacement is down, your acceleration will always be up. Here, when the displacement is up, your acceleration will always be down because it is performing SHM motion due to elasticity. Okay, like this,
Yes.
like pendulum only. When I stretch it here, the
Okay.
acceleration will be seen in this side.
Yes, ma'am.
Any doubts?
No, ma'am.
Okay, let me show you this particular thing again in the graph now. Okay, so that you will understand this clearly. Okay.
Okay, ma'am.
Check. This is the graphical. Anything you want to ask?
No, I'm just like going through the
Yeah, please check. Please check. It's okay.
bill.
Any doubts?
No, ma'am.
The same thing I had explained.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. If you want to go for velocity time graph, this was displacement. Okay. If you want to go for
Okay.
velocity time graph, it will be just vice versa of this. Because velocity increases. I'm shaping it here only so that you can compare. Check now. Okay. When the displacement is up, velocity will be here. Check this. Velocity will be start from 0, right? When it was up. Isn't it? Because here the highest point of potential energy is highest. So now it will start converting into kinetic energy. So from here it will start converting into kinetic energy. Making sense?
Yes, ma'am.
Check Akshita, it's very important. When my pendulum is like this, you stretch it in the right side. Where will your velocity work? In the opposite direction. So when you are stretching it in this direction, it will be the velocity in the opposite direction. Making sense? How the graph is drawn?
Yes.
Any doubts now? Because I am stretching it and here my MGH is highest at extreme point. So my velocity is 0. So hence velocity will be 0 for this position. Correct? And acceleration will be maximum. That is G, which will be in this side. Correct? Akshita, are you there? Akshita?
Ma'am?
Yeah.
Hello, ma'am.
Yeah. Audible. Relax. So,
Okay.
did you understood the graph now? And this is the acceleration time graph for this. This is displacement time graph, this is velocity time graph, and this is acceleration time graph. Acceleration will start from opposite direction. just opposite of this wave. It is starting from +2, so the acceleration will start from -2. Why? Because when you are dragging it, when you are applying force in this direction, your acceleration is always supplied in this direction. Correct?
Yes, ma'am.
Any doubts?
No, ma'am. I will just write this down, ma'am. 1 second.
Sure. Write it. Be quick.
Yes, ma'am.
You want to write these two also?
Yes, ma'am.
Be fast. Are you done?
No, ma'am. 1 second, ma'am. I'm drawing the graph.
4 minutes.
4 मिनट बस 6 में लगाऊं गाड़ी
नहीं ठीक है
ये दोपहर जैसे
ठीक है
Yes, ma'am.
Done?
Yes, ma'am.
Okay, now after this, we are having finding the frequencies of a pendulum and mass on a spring. Okay, just pay attention. We have seen that the acceleration of the pendulum bob is given by acceleration is having the formula G over L into X. Okay, Akshita.
Yes, ma'am.
Okay, why is it so? Because we are aware F equals to okay, F equals to ma. Hence your A equals to F over m. Force is provided by the gravitational, and in the case of pendulum bob, m is the length of that. Okay,
Yes, ma'am.
this is the comparison. Just you can go through this in your free time. Okay, you can find out how they both are compared. Okay, so it is equal to G over L into X. And also we are aware that acceleration is omega square x, right?
Yes, ma'am.
Done. So therefore my minus omega square can be equals to G over L, or I can rewrite it as by simplifying omega equals to under root G over L. Clear?
Yes, ma'am.
Omega is also 2 pi f, that will be equal to under root G over L. So I can write my frequency as 1 over 2 pi under root G over L. Ultimately, I will get the time period as 2 pi under root L over G. Done. These are the two equations of time period and frequency of the oscillation.
Okay, ma'am.
Any doubts?
No, ma'am.
Okay, now compare it with the acceleration. Acceleration is minus k over m into x.
Yes, ma'am.
Done. Again, so my frequency will be 1 over 2 pi under root k over m. And your time period will be 2 pi under root m over k. So this is for spring mass system and this is for oscillation. Any doubts?
No, ma'am.
Sure?
Yes, ma'am.
Okay. So this is the particular thing all about SHM. Any equation can come, Akshita.
Okay, ma'am.
Okay, you just have to be aware of what is been asked. X equals to x naught sine omega t is your exact equation. Velocity is omega x naught all the time, and your acceleration is omega square x naught, where x naught is the amplitude of the wave.
Yes,
Omega
ma'am.
is the angular velocity, a is the acceleration. Okay,
Yes, ma'am.
any doubts in these equations? Omega you
No,
can
ma'am.
also apply 2 pi f. Also you can apply 2 pi over t, and you can connect all these equations to solve the numericals.
Yes, ma'am.
Okay. So this is it for the day. Akshita, let's meet tomorrow. Okay. Till the
Okay.
time, do prepare for these things.
Yes, ma'am.
Okay. Bye. Have a nice day.